Well, good afternoon, everyone. Welcome to our last seminar for the year. This is Professor Amy Bridget. She is a professor and head at Department of Aerospace Engineering at Penn State. You've been there 5 years, basically. And before that, she was at Georgia Tech in their aerospace department for about 20 years. Did her education at MIT, works in aviation and safety and human factors. I'll broadly classify it. I'm seeing if I can summarize without checking my notes here. Has a number of awards, works on a variety of committees, doing policy for this area, and is going to talk to us today about Rotorcraft. So I'm going to leave it at that and let you tell us what you're up to.
Thank you. I'm delighted to be here. Our semester ended a few weeks ago. I had a chance to rest up. I just salute anybody who at the end of the quarter with graduation looming in just a couple days is still standing, let alone able to make it to today's seminar. Thank you for coming. In the presentation today, I will be talking in part about work that's happening across the department. To give you an overview of Rotorcraft writ large and many of the concerns that we have with future Rotorcraft, seeing if they can really take off. Can they really happen? Is the full range of developments really there? But I will also take the presenter's prerogative and end on one aspect of this that's near and dear to my own heart, some of my own musings with it. And when we think Rotorcraft, we usually think of fairly terrestrial atmospheric vehicles. But first, let me just start by noting that Rotorcraft are enabling new methods of exploration. This is a picture of a dragonfly. The notion being that it will arrive at Titan somewhere around 2033. Be ejected out of its aeroshell and fly away. The drone itself is being created by Jack Plankalon, Sven Schmitz, and Jose Palacios at my lab, and they like to talk about how wonderful Titan is as an atmosphere. If you just flap your arms in the thick methane atmosphere and the reduced gravity, you could fly. Of course, you have to not mind breathing methane and being in a cryogenic temperature, but it is actually a wonderful place to fly a vehicle. And in doing so, it can carry a fairly large payload being prepared by Johns Hopkins as lead and a number of partners that can sense the very diverse geologic and other features of Titan. The Titan was selected because every place they go, they will find some new geology and have a lot of hope to look what they do. And what the drone brings here with the quadcopter, or it's actually an octocopter, it's got 4 stacks of two coaxial rotors, is that every flight, it will travel further than the Mars rovers have gone total ever combined. And so with it, they have a lot of exploration capability. Of course, then it needs to put out its solar, well, it's got a, what you call it, a thermal generator that'll need to, that it will then need to charge its batteries for a couple of days. But every couple of days, it can fly further than all Mars rovers. So we're now seeing that these multi-rotor vehicles are enabling amazing and new and powerful things. And indeed, often the vehicles that they enable not only get us to Titan to explore, but they can do new and funky things. This was our entrance into the Go Fly Challenge from Penn State called Blue Sparrow. And if you want to try and figure it out, imagine this is your seat. It's a motorcycle with 3 stacks of coaxial rotors over top. The power that we are now finding with rotors and enabling technologies, especially the electric propulsion, are enabling a wide range of vehicles. There's a variety of configurations with rotors pointing up, rotors pointing forward, lifting surfaces, rotors might tilt, the lifting surfaces might tilt. And with it, there's a variety of proposals for what used to be called urban air mobility, but that's no longer the correct term. It's now advanced air mobility. As somebody who lives out in the fields of rural Pennsylvania, I'm glad to think that it's not just urban people who have mobility issues. The visions that they paint for advanced air mobility are wild. I'm asked if I think they're going to happen the way that they say they're going to happen. And I realized preparing this talk today that I still had this slide from Airbus A-Cubed. That was at the time they were working on their Bahana aircraft. That in 2017, they issued this slide saying that we were going to have huge package delivery starting in 2019. And urban air, it's an update slide, urban air mobility by 2023. Now we have slipped, and I don't think that's just COVID. These are grand visions, and they are pushing the arc of the technology, and that's great. But there are also some things that we have as enablers, at the same time we have things that we have as concerns on what makes these vehicles possible and what might limit them from meeting these grand visions coming out of Silicon Valley and other creative billionaires. And so with my talk here today, I'd like to just review the big scope. Motivators for some of these advanced air mobility. We could transform transportation. I understand that better revisiting Seattle. It's been about 2 decades and your traffic appears to have gotten a lot worse. Yes, we understand that. The environment, the notion of moving to electric or other novel power sources. This is great. Enables new business cases that will really enable a wide range of new transportation systems. Great. Enablers, I already mentioned electric propulsion, new structural capabilities, and these systems are not entirely new. We can build on years of expertise in vertical lift. And this is one of the places where I like to talk about my home department. Penn State has one of 3 vertical lift and rotorcraft centers of excellence in the US. And it's a fairly large component of our department that's competitively recompeted every 5 years. It's grown significantly. And with it, there's a lot that has been developed by this community about the things specific to rotorcraft. There's much that's known. There's still some that remains unknown in the basic aerodynamics. So, for example, when we look at a blade, this here is the rotor hub. Imagine that you would have blades coming off of it. When you look at the blade, I'd say the outer 95% of the blade is pretty well modeled by many of the computational models we have and the experimental correlates to it. But the rotor hub itself is generating interesting things, poking up above the center top of the vehicle, creating large vortices that come back and interact with the fuselage, and sometimes even the tail rotor. And so this is one of the areas that we are finding that we're focusing on. It's hard to test. We're actually doing it in the big laboratory. Other things that come up with modeling the aerodynamics of the rotorcraft include the work that we're doing with the Navy on ship airway modeling. If you have a ship in a busy, in a windy situation, moving forward, the ship itself is creating a turbulent airflow around it that we would like, in the midst of all that, to land a rotorcraft that, especially if it's large, will add to the turbulence and add to it further. And finally, we'd like to not only understand it, but understand it well enough to enable both manual and automatic landings in those conditions where you're not only in turbulence, you're impacting and helping shape the turbulence. By the way, other things that come off of some of these aerodynamic efforts include notions of extending it to look at wind turbines, the rotors that have to be upright. With our recent hire of Mark Miller, especially Schmitz with the work in rotorcraft. And in many cases, looking at more active and stop rotor concepts and how their aerodynamics work. This has been a classic theme in our vertical lift and rotorcraft center of excellence. We're also finding that the other classic themes that we've had, enhanced performance, increased reliability, the interior noise and vibration control, not just for the sake of passenger comfort, but for the sake of fatigue life of the vehicle structures, not getting shaken apart. Like NAVFirst environment is survivability. These things all remain true, especially whenever you move to a new vehicle and you discover that these issues come up. But there's a lot of things that are now changing as well, and these will be some of the concerns that I will talk about next. When you look at radically new designs, as I said, rotors going up, rotors going forward, rotors tilting, lifting surfaces, all interacting with each other. The rotor noise and public acceptance is something that we have a large focus on, autonomy in general and autonomy and safety. And so with this then, the concerns that I'll raise, are these really ready to take off in every sense? The physical takeoff is actually pretty easy. But they make the case for their continued and safe operation. There we have some concerns, and I'll start with working ice. So given your association with Mike Bragg, I don't know how much I need to talk about icing. I'll quickly note that ice can be a very bad thing when it forms on the field. Pennsylvania, especially in the winter, we are intimate with the notion that ice can form slowly, a little bit of rime ice. Has that perturbation on your surface, degrading the performance. In really bad cases, you can get glaze ice that forms the big horns. And this you can't call aerodynamic or control. It's actually a fairly complex multi-physics problem in that there's a number of factors that go with it. I'm still showing screen. The temperature, ambient temperature of the air and the water, the amount of liquid water content, the diameter of the water drop, and the impact velocity all can share. So some of the first efforts is just creating the mechanism for better understanding, modeling its formation computationally, and then being able to experimentally justify it without needing to wait a couple of years to get into the ice research tunnel at NASA Glenn. And so this is something that we've been working on. Looking just at one of the classic test cases, an NACA 0012. The reference airshade published by NASA shows that this sort of icing in one particular case, this would be your rime icing, which we have been managing to duplicate with our computational methods, and is shown in blue here, case 37 in our adverse environment research test facility. Rime icing, not too hard. Glaze icing, woo, yes, victory. And so being able to get to the point of understanding the sorts of conditions in which these the sorts of conditions in which these happen and being able to characterize them in the system. This happens on both your fixed wing and also on your rotors. And with that, we have both the linear flow facility with the icing environment, as well as a rotor test stand with the icing environment. And some cases where we've started looking at some of these new multi-rotor, multi-copter type things include this case here, where we took off one of the arms of one of the larger drones. This is the sort of size of drone that you could envision doing some package delivery and sticking it in our icing wing tube. Now, what's interesting about icing is first it accumulates, and that sounds bad. Aerodynamic performance, and these rotors are not just your lift, they are also your control, your actuation, your stability. But things get much worse when the ice starts cracking on a rotor. Rotor spinning. One rotor stuck line off, you now have a severely unloaded asymmetric thing that will shake. Because just look at the time scale here, we put this as a 1 point, next sample, just over 1 millisecond later, we can see the crack visible, and then just under 3 milliseconds from that initial point, it shed ice in fairly discrete ways. Now, looking at this, when I first saw these results, this is the work of Jose Palacios here, I said, oh, so what did you look at? Did you look at the rotor hub loads and so forth? And he said, no, these vehicles, we have motor controllers that you tell them what RPM and they track the RPM. It's intrinsic to this type of motor and system. And so we were tracking the amps into the motor with it working, pulling to get out the sufficient amps to overcome the drag of the ice. Until it shed, at which point our control system, the speed controller in the motor, freaked out, went up to 70.6 amps, And either in this test or next one, the motor caught on fire as with the spikes of amps going through it. So that was actually our failure mode. Now, if the motor had actually been able to be shut off, we still would have had a spinning motor that was asymmetrically loaded. So choose your poison on which thing will bring you down first. So the icing is interesting to us because on the large aircraft, icing protection systems are intrinsic. Those flying a small aircraft, a 172, my husband and I have a Bonanza, we just do not fly in icing conditions. And in Pennsylvania, that sometimes we don't fly for a couple of weeks. On the larger aircraft, they will build in protection systems that have some basis of power and heat to prevent ice or to crack off the ice or melt off the ice. But on these vehicles, electric power is in short supply. And the notion of needing the power system required for icing protection could be equivalent to the power needed for the flight. That's a rough order of magnitude. So we'll just point out the icing, flight and icing conditions can be a problem. It can even be a lovely day on the ground, but all you need is some ice, some liquid water content in the air up near a freezing level, which doesn't need to be too far above you, and you can have these icing conditions. Another factor, and at Penn State, we're particularly blessed with several faculty. We say we have 3 winners of the Aeroacoustics Award on our faculty and another recently hired out of NASA Langley. And they're looking at noise in general. Now, I'm just a stinking cockpit designer. They've had to coach me, hopefully, on these slides. But what I've learned from them is that aeroacoustics is a case where we can rewrite fluid mechanics, Navier-Stokes equation, as a wave equation. And with that, we can highlight that there's 3 different sources of noise. The thickness noise just comes from displacing the air. The loading noise comes from accelerating force, which means that you're loading something. And when you're flying with these multi-rotor vehicles, the loading on the rotor is your control mechanism, it's your actuator. So this includes the blade vehicle interaction noise of what's coming off the blades, also then impacting any aspects of the fuselage or other surfaces around. And then the quadrifoil noise is fortunately not as big a factor in this flight condition. But loading noise, thickness noise, but especially loading noise is a significant concern. Now, using this Fox-Hawking equation as the basis, Ken Brentner has created a computational prediction system that he calls WAP-WAP. Think computational fluid dynamics only solving the wave equation instead of the straight Navier-Stokes. And these results here are just intended to highlight some work that he's done with the FAA and other industry, looking at how accurately can WAP-WAP predict noise. For 3 different helicopters, the Robinson R66, the Airbus A350, and the Bell 407, we looked at 2 different flight conditions, level flight and a 6-degree descent, which is a case in which the rotor vortices tend to interact with the rest of the vehicle in that descent. And we have flight test data and prediction, flight test data and prediction. How are we doing? We're doing pretty good. It's an amazing advance. Maybe we've been waiting on Moore's law to catch up with the Hawking equation. But yeah, we now have the ability to computationally predict with fairly good accuracy the Rotorcraft. What do we do with this? Well, there's a couple of things. First, we look at the vehicle design. The effective tip speed, and including in this some unsteadiness modeled by having a different alpha with the rotors that goes around. Looked at 3 different cases. All 3 provide, these are actually, I believe, propellers, vertical rotors, that all provide the same thrust. So we're looking at the noise out of the same thrust. And we could make it 3 blades with a tip speed of Mach 0.7, 6 blades with a tip speed of Mach 0.4, or 6 blades that are more lightly loaded, tip speed of Mach 0.3, a little bigger diameter. And what we see here is the distribution of noise around the vehicle. Which vehicle is worse for noise? The top. Guess which propeller is the most aerodynamically efficient? The top. Indeed, some of talking with Ken and Eric Greenwood about these results relative to the Joby release recently that they flew it and it was insanely quiet. They've gone more this route because they're worried about community acceptance of noise. Less efficient, requires more energy, and recall a continuing theme through everything here that the batteries are the limiting factor on range. So you're making less efficient use of that precious energy storage if you want to get the noise down. Now, one thing you can do is design a propeller. Another thing that we've been exploring is, can you put the rotors locate them in a way where they might be constructively interfering with each other, straighten a line at one particular spacing that happens to interfere, or could you perhaps stagger them in a way that principles of constructive and destructive interference make the noise impact on the ground plane under the vehicle much lower? The answer is yes. You can make some very specific design choices. Of course, the structures people might say, how am I going to mount the propellers that way? But you can dramatically reduce the noise impact. And finally, another thing that we can look at is rapid analysis of flight procedures. Bring in, here Eric Greenwood is taking in noise measurements or detailed computational measures of noise and making them into a quick reduced order model. It's to develop a database. We're exploring reduced order modeling methods here as well, such that we can be building it into the autonomy to understand, if you fly this trajectory, this will be your acoustic. And with this, we're now working to do the inverse of that, the design problem. What trajectory should I fly to get to my destination? Well, meeting at least some constraints on the noise impact. The final extension that isn't published or out yet is autonomy guy, Eric Johnson, and the acoustics guy, Eric Greenwood, now working together, making a large hexacopter in which they can also do some things. One is they can build into the control algorithm an understanding of, if you load the rotors up this much at any instant, you will create this much noise, and look at adaptive control mechanisms that will reduce or limit loading the rotors unnecessarily, even if that means slightly degrading the speed at which you're tracking performance. Ease back on the tracking performance so you don't load the rotors up at critical moments in an acoustic sense when you're right over a sensitive population. And likewise, we're looking at controlling the relative phase of the rotors, where they are relative to each other, and seeing if we can use that active control of the phase of the rotors to decrease noise. In actual, the theory says it should work, but can you actually precisely control your rotors sufficiently to get that noise reduction? Great. Are they ready to take off? There are some other things. Autonomy overall is, we use that as kind of a common term. In aerospace, we usually use that to mean to talk about control, guidance, path planning, and perhaps decision making. And here I'll just talk about some advances, especially on the guidance control aspect for these multi-rotor vehicles. This is work that dates back to Eric Johnson's work at Georgia Tech, where the notion at the time, I'm going to do a quick tutorial on model reference adaptive control here. The notion at the time was that if we've got a dynamic plan, we've got some notion of the inverse model of that plan, put the two of them together and we get the ITAC. One. Awesome. So if we've got one here, we put a reference model. I would like you to behave like this, critically damped or slightly under damped second order response. That's what I want your closed-loop behavior to look like. Then just put that reference model in here, put a little PD controller to keep steering you back to that reference model behavior. Awesome. Okay, there is one problem, that is that you never know your dynamic conversion very well. So let's use a neural net to train the dynamic conversion or correct for errors in the dynamic. This was the theory in the early 90s when Eric was starting in his graduate studies, and quickly they realized that there were some problems, and then they got the backpropagation neural net going. But at the time, Eric was working on the X-33 single stage to orbit vehicle, which goes through such dramatic different atmospheric conditions that you needed the dynamic conversion. But to do it, it also was saturating its actuators. You could give it a command to move its actuators this much. You didn't actually get that. And at that point, your neural net is going, hey, you asked it for a bunch of stuff, and it starts learning not the plant dynamics, but the saturation limit, which is not good. So some of the innovation that we've been using ever since has become our default standard in the Eric Johnson's UAS lab is to go and add yet another, this is the last block I'm going to add here comes, which is to add in the notion that you look at what's commanded to the vehicle, you look at what you're actually getting out, you look at what you were expecting to go in, as you and the X actual state as best measure as you can, would be a comparison of what's coming out, or what you asked for, what you got with your command signal, can feed in actuator if you want to compare a commanded actuator and actual and X, and recognize cases where you say, hey, reference model, stop being unfair. You're asking this vehicle to do more than it can do. And you back off the overall expectation of reference model that is supposed to control. This was the game changer for us that made it so that this system, even though they call it neural net, these days I think it might be called machine learning. I like to point out that aerospace was like a decade or two ahead of its time, doing backpropagation neural net control, just called it that and not machine learning. And this was a real game changer for us in multiple ways. Indeed, Eric, the place in the place I'll show, in many cases, Eric enjoys just doing dynamic conversion, assuming the identity matrix is the plant dynamics. He says he just needs to get the sign on the diagonal ones correct, plus or negative. And it will learn from this. So just to illustrate, some of this work is actually coming from Eric's work back at Georgia Tech. He moved with me a few years ago. And this was looking at fault tolerant control. In this case, we took this airplane.
Has released, but it has not released from.
And we tried to blow off the wing. I'll take it. There we go. Okay, so we blew off the right wing in this case. We did not tell the flight control system this was going to happen. The impact on the performance was so severe that it had lost its right aileron, it had just a wee bit of right aileron on one side. The only way that it could prevent roll was to do the opposite aileron pull up, meaning that it could not maintain altitude that was in the general descent. Likewise, the vehicle is now so asymmetric that it has started and initiated a bit of a cuckoid mode. You can no longer decouple lateral and longitudinal. And we saw the initial transition where it did a quick wing rock. But ever since then, within these few seconds here, this is how stable it is. So we see this sort of control as an enabler. First off, it's a sign that it can handle sudden failure modes and flight conditions. But to us, it's also turned into a case where you can strap it on a vehicle and with minimal system ID or modeling and have flight test. With this, the UAS lab is moving from not just testing UAS to also the UAS. We're talking about putting a hot wire on top of one of the big wings for flight testing. Or I mentioned before, the aeroacoustics, that the UAS can now do the precise flight control that can be the test vehicle for other disciplines. Some of the advances that come up in here as well, some other things that have been a bit more recent since blowing off the wing. This is the case working with Scion. Let me see if I can skim it forward, looking over my shoulder. So this is the standard vehicle here was a single person, small light helicopter, but we took the person out of it. And so now it's flying unmanned, and its task is to find using vision only and land using vision only on the flatbed behind it. Regardless, without knowing ahead of time where the truck was going or what speed it would be going at. And so this is another case using the same adaptive control laws we had before, where now we're integrating in the visual motion in more detail. As we get over the flatbed truck here, you can see the target made to help with the visual processing. So really coupling in the vision with the control. And some of the current work that we're doing includes things like the Navy's been ramping up every year our task on being able to land on ships. At this point, we have taken the RMAX out to land on boats near Penn State, but more recently we took a Logo 800 out landing on Navy ships in high seas by vision with respect to vision only. And in future, they're asking us to do it in ways where there is no necessary target or anything on the vehicle. In other words, can you go land this drone on a vehicle that doesn't know you're doing it? Or can you go put a sticker on a moving vehicle, car, boat, whatever, or who knows what the military wants to do, without them knowing what you want to. So I point these out as some of the enablers, that this is a very powerful capability for many things. However, for those of you who don't realize that that guy is my husband, and that's why I followed me from Georgia Tech. In case you want to know what debates at home are like, I talk about safety all the time. And when we talk about safety, we have to recognize that, sure, you start by proving you have the capability that can work in ideal conditions. If that doesn't work, you don't have anything. But that's not the stopping point. Then you get the components to be reliable. Great, good and necessary. But after that, you get into cases where you have to think more cogently and specifically about things like, am I unnecessarily making complex spaghetti code that is going to freak out when my ADIRU fails? This happened twice to Qantas in an A330. Or have other complexity issues that make it hard to have new capabilities and to prove their safety. Will it really be able to adapt to circumstances? Interactive. I personally don't do military research, but I have followed the US Air Force chief scientists. They have a consistent method of saying that they do not want vehicles that operate autonomously. They want every agent and their team, human or machine, to be part of a team that is coordinated. Indeed, with autonomous vehicles, some of their concerns is the command and control chain for things like targeting and firing decisions, and making certain that the entire team is synchronized and the final decisions are correct is a major emphasis to them. And so when they talk about a drone, they want it to be something that is in communication, coordination with them, reporting its situation and its capabilities, and responding to requests for new missions, changes in its parameters. And with this, changes in how we operate infrastructure. This leads to an overall principle of designing for safety, which includes, from my point of view, things that have now reached up to the point of ethical question. And I'll return to ethics in a bit. Now, indeed, aerospace uses the word autonomy in a very strange way. One definition of autonomy is that an autonomous teammate is one who goes away and does their own thing. And this is how aerospace has tended to describe autonomy. Look at this drone. It can go upright for 6 hours independently. There are some places that talk about how long it can operate. Or look at this drone. It can go do this mission as long as everything's working well. All on its own. But one time, revamping, thinking I need to refresh my literature review, I looked at autonomous teammate and I didn't realize that I was searching on an organizational management database. a very different definition of what an autonomous teammate is. Autonomous teammate calls for help when it reaches its boundary conditions. Okay. Current day drones are good here. They're not good here. They're not good at recognizing I can't operate in this flight condition. Or they're only good if we think about it ahead of time. We plan for it and we try to pre-program in every single condition that it can operate. But from the organizational management point of view, an autonomous teammate may be a robot that is mopping the floor, the simplest thing. But it comes to you and says, something's the matter here. I need help. And this is a huge difference from the point of view of safety and its role within the team. Because if it cannot call for help, then it needs whoever's responsible for its outcome to monitor it at least as fast as the subordinate can screw up. By the way, for auto flight, that is continuous. And it needs for the supervisor to be able to intervene in whatever interval goes with the dynamics of the vessel. Indeed, from the supervisor's point of view, the subordinate is triggering the supervisor's off nominal conditions. You have icing form messes with the auto flight, that clicks off, and now it's the pilot's problem. Now, by the way, I've learned in the last 5 years that monitoring and intervention are hard. I would much rather be flying the vehicle than doing the monitoring and intervention. These are not easy things. Ask your department chair. Yet this is where our vision of autonomy in aerospace has ended up. And aerospace, especially aviation, has a long and glorious history in looking at the question of autonomy and developing it, and also looking at where's the pilot fit in. Indeed, the so-called Mamba list, men are better at, machines are better at, obviously predates political correctness. It goes back to a 1951 National Academy report, Human Engineering for an Effective Air Navigation and Traffic Control System. This is the basis for supervisory control, not just in aviation, but in many domains. It's been widely cited, and I think most engineers looked at it and went, okay, that's what machines are good at. My research is going to focus on detection. I want to extend what the machine can do, right? We saw this as the challenge list. Likewise, it was commonly viewed as the basis of function allocation. All right, if that's what machines are good at, let's have them do that. If this is what men are good at, let's have them do this. And these debates continued through the decade. For example, when Autoland was being implemented, there is a conference, a workshop on it, and one person, presumably an engineer, said a conclusion seems to follow. If a suitable means is not provided to the pilot to enable him to land the aircraft, then a suitable means should be provided to prevent the pilot from interfering with the automation during the last critical phase. Okay, pretty sure this was an engineer. This one, Turcat, was a pilot. I believe he did the first flight of Concorde. And he said, we've been striving to retain the preponderance of control in the hands of the captain and his crew, not only in favor of their dignity, but also in favor of overall safety. We would like to see Autoland used as the autopilots used during cruise. That is to say, as an aid and contribution to rest rather than a new pain in the neck. And this, I just love these quotes because nothing's changed in 50 years since then. This still reflects, in large part, a common technology driven that wants to push the pilot away, and the view of the pilots that the autonomy can be a pain in the neck. Now, rather than join in this existential debate of roles, let's also just step back and look at it from the point of view of safety. Aviation does not allow for single plane failures. We don't make it so there's a wings fall off button. And instead, we talk about layers of defense. Sometimes now called the Swiss cheese model, which is the notion that there are always hazards when you fly and another safety critical elements. The question, you can never eliminate all the hazards from coming up or occurring. Instead, you build in layers of defense. You build in the reliability, the components, their ability to respond to the hazards. You build in the pilot's ability to monitor for and intervene. You build in safety systems and backup systems and so forth. And as you go up the chain, you can think of this as more and more organizational. Are the pilots trained? Is the maintenance trained? Was the design properly reviewed? Within this, fairly recent studies, now 2013, by the performance-based aviation rulemaking committee and the commercial aviation safety team reviewed pilot interaction with flight path management system, the automation, and they found that pilots mitigate safety and operational risks on a frequent basis to the point that the aviation system is designed to rely on them. Put another way, pilots do many things that aren't even articulated. And one of the things that I'll call out is we looked at this study, looked at several different sources of data, accident reports, major incident reports, voluntary reports by pilots and others to the aviation safety reporting system, and line operation safety audits where an observer rode along and observed an otherwise normal flight. These flights in green here represent normal flights. They were observed and no abnormality, no explicit safety issue that would be considered abnormal was in place. And this represents 10,000 flights within the continental United States by a range of carriers and on a range of their definition in this case of aircraft malfunction is anything that required pilot interaction during the flight so that the flight could continue to its destination. And it could range from anything from an engine fire, emergency landing at Philly, to a little blip when you turn off the APU and fire up your second engine that blows your a couple circuit breakers and you have to retoggle. So anything from the benign to the most, but anything where if you did not have a pilot there, you could not continue the flight. They had to intervene. The fact that aircraft malfunctions are viewed as the triggering cause in 55% of accidents is not really a surprise. But look at the green. 20%, and a more recent study has been tracking this in more detail and is now up the official number to 24%. The authors of the report. This means if you go and say to a pilot, "Hey, did you have any malfunctions this flight?" They'll say, "No, I didn't." And you're like, "But the flight data says that you toggled the circuit breakers." They're like, "Yeah, they blew a little bit, so I toggled." You're like, "Oh, I just asked you if you had a malfunction." They're like, "Huh? I deal with malfunctions all the time. If I'm doing a trip, a 3-day trip with 5 flights, I'm going to have to do something on average once per trip on at least one of those flights." This is part of the pilot's job. Indeed, the reason that the Boeing 777 and other modern aircraft have such incredible dispatch rates where they push back 99.7% of the time, have no maintenance issue, is because the Boeing 777 can be flown revenue flight without any significant operational changes without the auto throttle or the autopilot. If those things fail, hey, you still have pilots. Let's go for it. And it will be transparent to the passengers. So we've seen a bit on safety. In 20% of flights, something technical fails and the pilot resolves it. In 55% of accidents, something technical fails and the pilot can't successfully resolve the failure or control the situation. Now, I often hear that pilot error is a huge part of accidents. And this is sometimes expressed to me as, let's get rid of that pilot. They caused the accidents. Okay. Anybody familiar with Bayes' rule or other conditional probabilities here? Which is bigger, flights or accidents? Flights. Pilot saving the day, pilot not being able to save the day, and the other accidents where perhaps the pilot was more intimately connected. Okay, this is the big number of the fact that our system normally operates with all sorts of things happening that require some that have disturbances, hazard, perturbations come up. Some of them fairly benign, usually fairly benign, and the pilot is responding to them. By the way, after the MAX, I asked my students to go through the 737 MAX operator, flight crew operator manual, and just count the number of cases where there's dual redundancy in critical systems, and what is supposed to happen if there's a mismatch between the systems. The number is something like 35. It includes angle of attack, airspeed, pitch, roll, a whole host of other sensors that only have dual redundancy. And in the flight crew operations manual, it says if there's any discrepancy between those redundant systems, it will say to the pilot, pitch data in red, and then it'll say, and you got it. You got it in terms of control, but also you got it in terms of you get to figure out what your attitude is. Good job. So, all right. So from this, we further were trying to look at what is there anything that we see that really traces about how pilots use autonomy in current day operations and how it might relate to safety. And indeed, we found that there's a huge score of flight management system programming errors. Now, they don't lead to accidents necessarily. Right? This is a case where you're given a detailed reroute in flight and the altitude that you're going to climb to once you pass the storms, you enter one digit wrong. The good news about these is they're usually caught and caught fairly early. Pilots are very aware of them. Indeed, they are the subject of about a third of the aviation safety reporting system incident reports filed by air transport pilots. Oops, I put in 18,000 and I meant to put in 17,000 for the box. The one thing that we found that really tracks accidents being the worst, then major incidents, then ASRS reports, and then normal operations is pilot-pilot communication. And I realize this is just a hypothesis on my part based on the scant evidence we have. I really think there's something about two experts monitoring each other that is the secret sauce in making commercial aviation the safest system ever. So pilots right now, pretty good. Autonomy is increasingly pushing them away. Take the most current system, starting with the 777. The things the pilot needs to do, only things that really needs the pilot to do is to flip the power levers, one for each engine. Taxi, they decided they didn't want to automate the steering of the taxi. Taxi to the runway lineup. Then you press toga, take off, go around. And then it says raise the gear, and they didn't automate raising the gear. And then it says raise the flaps, and they didn't automate that. And then 18 hours later, it says lower the flaps. You can lower the gear, and then you need to taxi and then turn off. That in theory is it. Only about 10% of the flights can actually do that because of onboard failures, and as we saw, but also because of ATC reroutes, weather issues, and so on. But what we found then is we've given increasing authority to the machine to execute the action. Here, autoflight, you fly. But the responsibility for the outcome of the action is still assigned to the human operator in law, in federal aviation regulations. For air transport, it all comes back to Federal Aviation Regulation 91.3. The pilot in command has the sole authority and responsibility for the safe conduct of this flight, to the point that they can override any other part of the Federal Aviation Regulations to maintain safety. When you land, you're going to have to explain why you ignored it. But that is the core regulation. And if you fall back on that, you can break every other law as long as you can prove you are keeping things safe. But what this means is now pilot command is responsible, but they're just sitting there. They're just supposed to watch. This leads to two difficulties. The pragmatic, when the human operator reasonably monitor and intervene. When your job becomes that passive, we have problems with vigilance, with currency. We also have the ethics. Is it fair to expect the human to be responsible as they are being pushed further away? Is it fair to say to you that your job is to sit here and let that autoplay fly because it's more fuel efficient. But if something goes wrong, you're to blame. Is that really a fair and ethical position to have, especially in cases where it can be very hard and confusing? And usually when you're asked to intervene, it's a very bad thing. Engine fire, pitot tube side still burns. Now, I mentioned before, 1951, men are better at, machines are better at. That we came up with this Mamba list saying men are better at, machines are better at, and people have used that for 71 years as their basis for arguing to give more to the machine. It's just a pity they didn't read the next page of the same report, which said, we have taken the position that the human operators are poor monitors when all they have to do is watch the performance of automatic equipment. This was taken as such a de facto standard that they were just repeating it. Human performance is not good at passive monitoring. And so they argued that we should do something different. Where have we gone somewhat recently? Okay, this figure is about 3 or 4 years old now. The DARPA Alias program. This is the nice, beautiful glitch shot that Aurora Flight Sciences put out. They were to make a robotic co-pilot that they could just take out the seat, roll in the robot, and it would become a first officer. And what they roll in here is something that's a robot that reaches out and grabs the control column, pushes on the pedals, and grabs the throttle, and has cameras that can read the flight history. Okay. But I look at that and go, if I was that captain there, I do not want my first officer to take over flight. That's the fun part. I want my first officer to talk to air traffic control, to do the system checks on the engines, the hydraulics, and so forth, to tune the radios as we transition between different airspace, different air traffic control centers. That's what I want the first officer to do. And so the things that I'm trying to explore and articulate are cases that we can look at very different architectures and roles for the pilot. For example, I personally will put out that I think pilots can fly almost all the time. There's a couple of exceptions that we could debate. Should hand fly below 18,000 feet in air transport. Do the departure, 18,000 feet, you're into cruise airspace, you're in Class A airspace. Let the more fuel efficient auto flight take over, but you're up in big separations, things are usually pretty big. And as you descend during arrival down to 18,000 feet, let the pilot. If we want to automate anything, let's automate all the other stuff. The stuff that isn't fun, isn't sounds too, isn't joyful, isn't why pilots got into aviation in the first place. Automate the things that you do not need to maintain manual control skills for. But I realize those are fairly complex and cognitive tasks. That's no excuse for us as engineers. Oh, those ones be too hard to automate. Let's automate the flying. Another seminal study was actually from undersea vehicles, 1978, Sheridan and Berkeley. This is the same report that first proposed the notion of levels of automation. But in the same report, they mentioned that there's many different architectures on where the human is and what the human might do. And with this, I am now at a phase of life where I'm going around, cranky middle-aged woman going, we could do something different that doesn't set the pilot up. So with this, I hope I've covered some of the concerns we have with, are these vehicles, new funky vehicles with rotors based on increasing autonomy, ready to take off? And I welcome any thoughts or questions that you might have. That was our rotor test. Somebody left, put a DGI in there and thought that was fun. Okay, yes, thank you very much.
All right, thank you. I'm gonna have to, just one quick thing. I have to take off here shortly because I have to pick up my kids. So we have a thank you gift for you. Would you maybe be willing to field the questions?
Of course.
And by all means, ask questions for Amy, and
I can talk about this for hours, so I'm here for some. Yes, thank you so much for having me.
you.
It's been a wonderful day getting to meet you.
Okay. And there are probably gonna be some online questions as well.
Okay.
Great. Thank you.
All right. Yes, please. You hazard a comment about the 737 MAX safety issues and how that folds into this general topic.
Let me. There. I don't have enough time to describe all the layers of defense that broke down in the 737 MAX accident. If that makes sense. I'm currently chairing a National Academy study looking at emerging trends in aviation safety. This first year, we were told specifically to focus on air transport operations. And when asked why the national monitoring system for safety issues, looking at digital flight data recorder data, did not identify any issues, it's because it didn't happen in America. These sorts of accidents that are coming up now violate many layers, but some of them are ones that we historically took for granted. Pilot training, rigorous maintenance, and not dispatching airplanes that had been freaking out the previous flight, but also design choices that didn't give so much, didn't have creep in how much authority they would get the very powerful system. I better stop there.
And we can talk more after the recording is done. Any other questions?
Yes, I have a question. So I saw that you test the phantom in the water tunnels. Is that for dynamic testing or that's for flow-based?
The rotor hub we tested in the water tunnel.
Yes.
Yeah, and that was, we wanted to get it's a beautiful tunnel with nice PID so that we could really track vortices in detail while getting the Reynolds numbers that we needed to go. Yes.
I have a question for every section, so I'm just going to take one at a time and look at the very good. First section, where you talk about the wing coming up and autonomy or compute takes over. So you're taking care of flight. Now, how do you deal with that in a DAA, SAA situation in a heterogeneous airspace?
DAA.
You're deconflicting any other aircraft in your airspace while you're dealing with a wing coming off.
Yes. And there are plenty of interesting questions there. First off, if you look at modern air transport, if an airplane has a big enough problem like this, you clear the airspace quickly so that they have room to maneuver or not be able to maneuver as appropriate. And yeah, we can look at examples with control failures and so forth, where clearing the local airspace was necessary. So wing coming off isn't something that we're proposing should be happening frequently, but it is nice that the vehicle is able to at least keep the control going, allowing the other outer loop or lower bandwidth activities to then work to deconflict and spread out.
So does that make an assumption that if you have 100 drones per hub in a urban setting going at the same time in a 400 or below foot airspace, that you're going to have a communication system that can tell everyone in that airspace to get the hell out of Dodge?
Or we look at how we do separation, at how we do nominal separation to make certain that we do not have vehicles flying in situations where if one of them goes off kilter, it takes out neighboring aircraft immediately. That's one of the things that goes with separation functions. Working in the air transport side, for example, some of the things that I've done a lot of work on is the closest space parallel. San Francisco's runways are an exemplar of that. They're 750 feet apart. And as they created the single offset independent approaches, or SOIA, into it, we found that we could stagger the airplanes on these very close to space parallel approaches in instrument conditions so that they were essentially in each other's turn radiuses, so that they would be prepared for the sort of full-on blunder that might go with an engine failure on an outboard engine, if that makes sense. And so that was spacing an operation that in nominal cases spaces the airplanes so that if what we believe is a worst case event happens, they can't take each other into the center.
So my assumption is you're dealing with, they're people movers instead of product movers. Because product movers right now are 400 below. You want to watch for the glide ratio. You want to see what kinetic energy when it goes flat. But I'm also thinking about, there's going to be democratized space of the deliveries, the hobbyists, the air taxis, all in that space. How are you going to tell them all at once with a communication system that says, get the hell out of here because one's going down?
I am agreeing with you in that I think that we have not worked out the air traffic management protocol.
Mhm.
I think that if you then go and add the safety layer here of how do we manage the airspace, you'd say, there's a good reason we do not want airplanes at this density or these relative locations. What's interesting is that density is a loose metaphor. If you start structuring the airspace and the routing, you can actually get a much higher density. If everybody's in line, and a failure means they are going to drop out of the line into otherwise empty airspace. Great. So it's not necessarily density, but if it's not density, then it has to be agreeing to a common airspace structure and potential communications.
I'm going to stop there. I'll ask you later.
Yeah,
Oh,
yeah.
sure.
The vision of, hey, big sky, little airplane, just let them all have at it without needing to coordinate, breaks down. When you start getting to those sorts of densities, so it might work where I live, out in rural Pennsylvania, but I see how it would work here. And so there's operations and infrastructure questions that need to be answered. I just didn't get into some of the air traffic operations.
Any questions from online?
They're just, somebody asked one and somebody else answered it online, so
Okay,
we're golden.
all right. So I think we can continue this discussion over some snacks and coffee. So let's thank Amy one more time, and thank you so much.